Welcome to Generative AI Podcast. Today we're diving straight into something really fascinating, BitDistill.
Yeah, it's this new framework for taking these huge, large language models and seriously compressing them.
Right, like the Qwen models. They're getting crushed down to what they call 1.58-bit precision.
Which sounds kind of strange, right? 1.58 bits. But it basically means the weights can only be -1, 0, or 1. Ternary weights.
And the motivation behind this is pretty ambitious, isn't it?
Totally. It's about fundamentally changing how AI computes, moving away from, floating point math multiply and add, which is power hungry.
Towards add-only operations, using fixed points.
Exactly. Add only of fixed points. The potential energy and compute savings are just massive. Imagine running complex LLMs on much simpler hardware.
Like on edge devices, phones, sensors, that kind of thing.
That's the goal.
Okay, so our mission today is to really unpack the tech here. There are three core ideas that make this kind of extreme compression, this quantization, actually work without losing too much performance.
And the results are impressive. They're getting performance pretty close to the original full precision models.
But with huge efficiency gains.
Yeah, up to 10 times the memory savings, apparently. And significantly faster inference, like 2.65x faster, even just on regular CPUs.
Wow. Okay, but it wasn't easy. They mentioned that just applying standard techniques like quantization-aware training or QAT, it didn't scale well.
Right, that's the key problem they hit. Using standard QAT, what they call bitnet SFT, the performance gap compared to the full FP16 model actually got worse as the models got bigger.
So scaling was broken. Let's get into the mechanics. How do they actually enforce those one below one weights? There's some math involved.
There is. It starts with the quantization function, QW, takes the original weights, calculates a scaling factor, delta, which is just the average absolute value of the weights.
Okay, so it adapts based on the weight magnitudes.
Exactly. Then it uses this function called round clip. It essentially rounds the scaled weight to the nearest value in one lay and clips anything outside that range.
Simple enough in concept, but training with that. Isn't there an issue with gradients? Because rounding isn't smooth.
Precisely. That rounding operation is non-differentiable. You can't calculate a proper gradient for backpropagation.
So how do they train it?
They have to use an approximation technique. It's called the straight-through estimator, or STE.
Ah, STE. So it basically pretends the gradient is, 1 during the backward pass, even though the forward pass has that hard step.
Yeah, that's the gist. It lets the gradients flow back through the network, allowing the weights before the quantization step to be updated, even with that mathematical hurdle. It's a necessary trick for training these low-bit networks.
Okay, so they have the math and the gradient trick. But you mentioned stability issues persisted. What was the first big fix, stage 1?
Right, stage 1 is about modeling refinement. The core problem was exploding variance in the activations. Low-bit models are sensitive, and if the signals get too large, the training just collapses.
Makes sense. So how did they control the variance?
They introduced specific normalization layers called SubLN. That's sublayer normalization.
Not just standard layer norm.
No, these are placed strategically inside the transformer blocks. Specifically, right before the output projection layers in both the multi-head attention module and the feed-forward network.
Ah, so they stabilize the hidden states just before they hit those quantized weight layers, like a preemptive dampening.
Exactly. It stabilizes the variance right where matters most for the quantized layers. A very surgical fix.
Okay, SubLN tackles stability, but we still have the scaling problem. That brings us to stage 2, continual pre-training. How does this help? This sounds like just more training.
Well, it's a specific kind of pre-training, almost like a warm-up stage. The analysis shows it fundamentally shifts the distribution of the model's weights.
How so? From what to what?
So typically weights start out kind of like a Gaussian bell curve. This stage pushes them towards a distribution more suitable for ternary quantization. They call it a bitnet-like distribution.
And what does that look like?
The weights get heavily concentrated, very close to the transition points near MIGO 1, near 0, and near 1.
Okay. Why is that specific distribution helpful?
Because having weights pre-positioned near those target values makes the final quantization step during fine-tuning much more effective. It primes the model to actually fit the downstream data well, even with the harsh 1.58-bit constraint. It fixes the scaling issue.
Got it. So SubLN for stability, continual pre-training for scalability by shaping the weights. Now, stage 3, Distillation-based fine-tuning. This is where the magic happens to recover performance, right? Using a teacher model.
Exactly. You take the original high-performance FP16 model as the teacher and the 1.58-bit model as the student. The goal is to transfer the teacher's knowledge.
How do they transfer that knowledge? What are the techniques?
They use two main distillation methods. First, logits distillation. This focuses on the output. It uses Kullback-Leibler divergence, DKL, to make the student model's output probability distribution match the teacher's distribution.
So matching the final predictions makes sense. What's the second one?
The second is multi-head attention distillation. This goes deeper, looking inside the model. It compares the attention patterns, how different parts of the input relate to each other across the query, key, and value projections. It's about capturing finer structural knowledge, similar to what Mini-LM does.
Interesting. So it's not just about the final answer, but how the model arrives at it.
Precisely. Capturing those internal mechanics is key for the small model to mimic the larger one effectively.
And the final training objective just combines everything.
Yep. The total loss is the standard task loss, like cross-entropy, plus terms for the logits distillation and the attention distillation, weighted by some hyperparameters, lambda and gamma.
So putting it all together, SubLN for stability, pre-training for weight distribution and scaling, and multi-stage distillation for performance recovery. It's quite a comprehensive approach.
It really is. It provides a robust way to actually make these extremely low-bit models viable, which wasn't really feasible with simpler methods, especially at scale.
And what's maybe most intriguing is they found that the better the FP16 teacher model, the bigger the gains for the little 1.58-bit student. Sometimes the student even surpassed FP16 models of its own size.
Yeah, that points to the power of distillation when done right.
Which leads to a final thought for you, our listener. If these super efficient sub-2-bit models really take off, but their success hinges on having even better full precision models to teach them, what does that imply? How much effort needs to go into co-developing specialized hardware and the training pipelines for these teacher models to truly unlock this add-only compute revolution at the edge?
That's a great question. It suggests the future isn't just about tiny models, but the whole ecosystem needed to create and train them. Something to definitely think about.